This is B. Naresh, working as assistant professor in EC department. Today's topic is positive peak and negative peak clippers. So before going to this positive peak and negative peak clippers, first I'm going to define what is a clipper. The clipper is defined as it is an electronic circuit. It can be used to remove or attenuate some portion of given arbitrary signal, either in a positive portion or a negative portion or in both the portions here. From that point of view, the clipper is also called as a limited circuit. So in this clipper, it limits the amplitude of a given input signal. Hence, this clipper is also called as voltage limited circuit here. So, and based on the definition of the clipper, it is classified into two types of the clipping circuits here. So one is series clippers, another one is shunt clippers. So here the shunt clippers is also called as the parallel clippers here. So before going to this clippers analysis, then how to design a clipper circuit. To process this clipper operation, here we are going to use a PN junction diode. By using this PN junction diode, we are going to design either series clipper or a shunt clippers. So how we can say that either it is a series clipper or a shunt clipper. That is based on the utilization of the diode in a circuit. Means the output is in series with a diode or the output is parallel with a PN junction diode. Based on that, we are classifying as the clippers are two types, series clippers as well as your shunt clippers. In that, again, so here I'm showing that what is a series clipper here. So in this series clipper, it contains a diode in series with the load connected across the end of the circuit. Means, so from this circuit, we are going to observe the response of given clipper circuit across the load resistance here. If you want to design a shunt clipper, the shunt clipper contains a diode that is parallel with a resistive load here, or the output is in parallel with a diode here, and that type of the circuit is called as a shunt clipper circuit here. And these are the different classifications here. So today here I'm going to explain the shunt clippers analysis. So in that, the shunt clipper is again classified into two types. One is positive peak clipper, another one is negative peak clipper. So based on the definition of the clipper, either it attenuates or limits the some portion of given arbitrary input signal here. From that response, we are classifying the shunt clipper as again two types here. So one is a positive peak clipper, another one is a negative peak clipper. And again, this positive and negative peak clippers again classified as one is the positive peak clipper with a zero reference. One is positive peak clipper with above reference and a positive peak clipper with a below reference. So means the clipper is reference with a means the some reference with the DC signal. The DC signal is either zero or the DC signal here it is called as the positive voltage. And in the third case, the DC signal is a negative voltage. So if the DC signal is a zero, means we are not approaching any signal, DC signal to and this across the diode. The type of the circuit is called as a positive peak clipper with a zero reference. And across the diode, if we connected the some DC voltage, and that DC voltage is a positive DC voltage, and that type of the circuit is called as positive peak clipper with above reference voltage. And if the diode is connected along with a negative DC reference voltage, and that type of the circuit is called as positive peak clipper with a below reference. And again, the shunt clipper is again classified as a negative peak clipper also. In that negative peak clipper also, again we are classifying as the three types. Negative peak clipper with a zero reference, negative peak clipper with a above reference, and a negative peak clipper with a below reference. So how we can say that the shunt clippers, again the two types means the based on the utilization of the diode in a circuit, and based on that operation we are classifying these two types, positive peak clipper as well as your negative peak clipper. So we are going to discuss here now why it is called as a positive peak clipper and why it is called as a negative peak clipper with a zero reference voltages here. Now that I'm showing here, so if you observe this graphical representations here, in a first case, and this is our given input signal, and this input signal contains both the peaks, positive peak, and this is called as a positive peak, and here this is negative peak. And when this type of the signal is passing through the clipper, let us assume that this type of the input signal is passing through the clipper circuit, it attenuates or limits the positive peak. So let us take this is the response of clipper circuit. From this response, we can understand that this response, in this given response, it attenuates the positive portion and it allows the negative peak as it is of the given input signal. From this point or from this response, this type of the clipper circuit is called as the positive peak clipper with a zero reference voltage. Similarly, in the second case, if you observe, again, let us consider this is a given input signal. And again, this input signal contains both the peaks, that is positive peak as well as a negative peak. When this type of the signal is passing to some clipping circuit, and that clipping circuit allows the positive portion and attenuates the negative portion. So this type of the response here I represented here, and based on this response, that given circuit is called as negative peak clipper with a zero reference voltage. So these are the two different cases. Here I shown that some graphical representation of the what is a clipper. Either it attenuates the positive portion or it attenuates the negative portion. But some of the clippers attenuates at the both the levels, means positive portion as well as your negative portion. So we'll see in detail one by one here. Now coming to this, so here I'm going to use the shunt clippers. So what is the meaning of shunt clippers? The output voltage measured across the diode, or the load resistance is a parallel with the diode. So in this case, here I consider that this is the PN junction diode. This PN junction diode contains this is the anode, and here this polarity is represented as the cathode. And here we are going to apply a input signal, and that input signal is a AC signal, that is nothing but a sinusoidal nature here. Hence, it contains both the peaks, positive peak and negative peak. And the response or output voltage is measured across the diode. So hence, the output voltage I'm going to connect across the nodes of this diodes here. And here this input signal is passing through this resistor R to limit the flow of current, and diode is shunted with respect to your output voltage. Hence, this type of the clipper is belongs to your shunt clippers here. Now, so based on the utilization of the diode, in this case, this anode is connected to inputs, a positive pole of the battery, and a cathode is connected to negative pole of your given input signal here. So here, anode is connected to positive energy, and a cathode is connected to negative energy here. Or we can also connect in a different fashion, like if the cathode is connected to positive energy or anode is connected to negative energy. So based on this construction, it processes some operation. So from that response, we can say that this type of the clipper either attenuates the either positive portion or your negative portion here. So based on that limitation of the amplitude of a given input signal, we can say that either it is acts as a positive peak clipper or a negative peak clipper. So here this circuit shows the circuit diagram for positive peak clipper with a zero reference voltage. So here I am not connected any DC source along with this diode, hence it is called as a zero reference voltage. So in this positive peak clipper, so what is the definition of the positive peak clipper? Positive peak clipper removes or attenuates positive portion of given input signal and allows the negative portion. So that type of the process is done by the positive peak clippers here. So now we are going to observe how it removes the positive portion of a given input signal and how it allows the negative portion of a given input signal. So before going to this, analyze this circuit operation. So first here I am going to recall the diode operation here. In this case, and we know that when a PN junction or a diode, and this PN junction diode contain the two terminals, anode as well as cathode. And this is the symbolic representation of the PN junction diode. And here it is represented as anode and it is represented as cathode. When anode is connected to positive pole of the battery, so here I consider the DC source and you can also connect the AC source, and a negative pole of the battery, this cathode is connected to negative pole of the battery, then we can say that the diode becomes forward bias. We can say that the diode becomes forward bias. If it is a forward bias under the ideal condition, so in the two types of the properties, ideal and practical. So when the diode is acts under the forward bias and it is replaced with a short circuit, and at this point the output voltage is represented as zero under the ideal condition. Suppose if it is a practical diode under the forward bias, then it is replaced with the equivalent circuit. What is the equivalent circuit? Diode is replaced with a short circuit, along with it contains a cut-in voltage of PN junction diode. It is represented as V gamma. So this is the equivalent circuit under the practical diode when the diode acts as a forward bias. Under this condition, the output voltage across this diode is represented as cut-in voltage. So hence it is represented as V0 is equal to V gamma. So where the V gamma is the cut-in voltage of the diode. So here the diode is made up with a material, either silicon or a germanium. If the diode is made up with a silicon, the cut-in voltage for silicon diode is 0.7. If the diode is made up with a germanium material, the cut-in voltage for germanium is 0.3. So, and this is the conditions when the diode is forward bias. So this type of analysis we are going to apply for this circuit. Similarly, when let's take this again PN junction diode, it contains two terminals, anode and cathode. If anode is connected to negative pole of the battery and a cathode is connected to positive pole of the battery, then we can say that the diode acts as a reverse bias. If it is a reverse bias, so if it is a reverse bias, the current is not flowing across the PN junction diode. Hence, the diode is replaced with the open circuit. So hence, if the diode is reverse bias, That is replaced with a open circuit under the ideal condition or a practical condition. Hence, the output voltage across this diode is approximately equal to your applied input voltage. So, hence, based on this diode operation, now we need to analyze the operation of this clipper circuit. Based on that clipper circuit, we need to identify the type of the clipper. Either it belongs to your positive peak clipper or a negative peak clipper. And again, you should remember one more point in this case. So whenever from these two analyses, under the forward bias and the reverse bias, we should make sure that the anode voltage must be greater than of cathode voltage. We should assume this point. The anode, where VA is the anode voltage, VK is the cathode voltage. If the anode voltage must be greater than of cathode voltage, then we can say that diode acts as a forward bias. Under this forward bias, now we can replace with a equivalent circuit. If it is ideal, simply it is a replace with a short circuit. This is ideal. If it is a practical, it is a replace with a short circuit along with some cut-in voltage is V gamma. Similarly, if VA is less than of VK, means anode voltage is less than of cathode voltage, diode acts as a reverse bias. If the anode voltage is less than of cathode voltage, diode enters with the reverse bias, hence it is replaced with the open circuit. So at this point, the current is represented as 0. When the diode is a reverse biased operation, the current flowing across the reverse biased PN junction diode is 0. Hence, the output voltage across the reverse biased diode is equal to your V. So based on these 2 points, we need to analyze the operation of this positive peak clipper circuit. Now let us consider this is the circuit, and here let us assume what happens here. And here we are going to apply, this is the input signal. So when we are passing this type of input signal, we are on the 2 peaks. One is positive peak, another one is negative peak here. And this is positive peak. Let us assume when a positive portion of given input signal passing through this diode D1. So what happens here means, so here this is positive portion with respect to this one, means cathode becomes your negative. So whenever a positive peak input signal passing through this diode, so the positive energy of a given input signal is connected to, this is the anode of diode, and a negative energy means with respect to this anode, this negative energy is connected to cathode. Hence, at this point, your D1 becomes your forward bias. If the D1 is a forward bias, now what is the equivalent circuit? Now this is your given input signal, plus and minus, and here, so let's say this is R1, and now, so we know that when the diode is a forward bias, it is replaced with a short circuit under the ideal condition. And if the diode is a forward bias, under the practical condition, it is replaced with a short circuit along with the cut-in voltage. Suppose here I draw the 2 models, and this is D1 is replaced with a short circuit. So if it is a short circuit, what happens? Some current is flowing. That current here it is represented as your I. Hence, it is represented as when the diode acts as a forward bias, then the current flowing across this network, and that current is represented as your I. At this point, now we are going to measure the V out, means the output voltage across this short circuit path. Under this ideal condition, what is the output voltage now? So during this positive off cycle, diode is replaced with a short circuit. Why? Because of that, the D1 is acts as a forward bias diode. Hence, the output voltage across the short circuit path is zero, and this is ideal condition. Let us take if it is a practical condition, and during the again this I was explained only the positive portion of your given input signal. And during the same positive portion of input signal, if I consider the practical diode, so let us take this is the resistance R, and if it is the practical diode, so under the forward bias, it is replaced with short circuit along with some cut-in voltage. The cut-in voltage is represented as your V gam. Hence, again, so during this positive portion of your given input signal, diode is acts as a short circuit. Hence, it allows the flow of current across this network. That current is represented as your I. And now we are going to measure the output voltage across this diode. So from this equivalent circuit, what is output voltage? V0 is directly proportional to your cut-in voltage of diode. Why? Because of that parallelly the voltage is same. But here the output voltage across the short circuit path, hence the voltage across the short circuit path is zero. This is ideal condition. But coming to your practical condition, the output voltage is measured across this short circuited diode. But here I consider that diode is a practical diode. For this practical diode, what is the output voltage? The output voltage is directly proportional to V gamma. Hence, the output voltage here it is represented as V gamma. Here I consider this is practical diode. So this is the operation during the positive portion of your given input signal. If you consider ideal diode, the output voltage is entire the positive portion, it is represented as 0. If you consider the practical diode, the output voltage is represented as V gamma. Similarly, now we need to analyze what happens during the negative off cycle here. So for this case, now let us consider, now I'm going to apply a negative portion here. So means let us consider when an input signal is a negative peak signal. Now for this case, so what happens means here the negative magnitude is passing through the anode with respect to the cathode, means the cathode is connected to your positive pole. So during this negative off cycle, so your diode becomes, so based on this approaching of your negative peak across the diode, so your anode is approaching to the negative energy and the cathode is approached to the positive energy. Hence, diode D1 becomes a reverse bias. So if the diode is a reverse bias, then we know that it is replaced with the open circuit here. It is replaced with the open circuit. Hence, here I am going to draw the equivalent model. So let us say this is the R and this is your input signal, and let us assume that a negative peak is passing through the circuit. So hence, and this is diode is replaced with D1 is replaced with open circuit. Now at this point, now we are going to observe the output voltage. Now from this equivalent circuit, now we need to determine the output voltage. So here from this network, what happened if it is an open circuit and during this cycle the current flowing across this network is 0. If the current is 0, but now we are going to observe this output voltage. This output voltage is parallel to this given input voltage. Hence, from this circuit, V0 is approximately equal to your applied input voltage. So what is applied input voltage here? The applied input voltage is negative portion here. So hence, so when a negative peak passing through this given circuit, diode is acts as a reverse bias. Hence, it is replaced with an open circuit. From that equivalent circuit, we observe that the output voltage is approximately equal to your given input signal here. So based on these two analyses during the positive portion and during the negative portion, then we need to draw the graphical response from that. So what we observed here, during the positive portion, the output voltage across the entire the positive duration is constant, that is V gamma or is 0. So if it is, we consider the practical diode, that is a V gamma. If I consider the ideal diode, the output voltage is 0. But during the negative off cycle, what is output voltage? That is directly proportional to your applied input voltage. Hence, the circuit is called as the positive peak clipper. And this is a theoretical analysis. Now I'm going to show the mathematical analysis. Before that, based on this all this representation during the positive portion and the negative portion, so here I drawn the graphical representation of positive peak clipper. So hence you consider this one. So this type of signal is attenuated here. So here this is positive portion is attenuated, and but it allows the negative portion. Hence this type of the response and this type of the circuit is called as positive peak clipper. Now, so mathematically I'm going to show you. Let us consider the same circuit, and here from this just can apply the KVL. So this is your input signal, and during this one let us take the current is flowing. So when the diode is forward bias, and from that I represented this equation, the input voltage is represented as, so here the current is, which current is flowing? I. So means V is equal to I into R. Hence I represented that VI is equal to I into R, along with under the practical circuit, when the diode is a forward bias, this diode is replaced with the equivalent model. This is the equivalent model. So what is this equivalent model? This is V gamma. So hence the voltage across this diode is represented as your V gamma cut-in voltage. Hence I represented as, from this loop the equation is the input voltage is equal to the current flowing across the resistance and the voltage drop. Means this current flowing means this is the voltage drop across this resistance. So what is the voltage drop across this resistance? V is equal to I into R. Hence the voltage drop across this resistance is represented as I into R, and similarly the voltage drop across this diode is equal to your current voltage, that is V gamma. So from this you should identify the I relation. So what is the I relation from this equation? So here it is represented as I is equal to, so Vi minus V gamma by R. So from this equation one, just you can identify the I relation current. So means I taken this outside, hence it becomes Vi minus V means, so from this IR is equal to Vi minus V gamma. So hence I is equal to Vi minus V gamma by R. The same relation I shown here. Again, from this circuit, from this equivalent circuit, what is the output voltage? V0 is directly proportional to your cut-in voltage of the diode. Hence, V0 is represented as V gamma. So just substitute this relation. From this relation, here I am going to observe. So how to write this equation? Vi is equal to I into R plus V gamma is replaced with V0. Hence, from this V0 is equal to Vi minus I into R. V0 is equal to Vi minus I into R. So that I shown here. Now by using this mathematical relation, now we are going to observe what happens during the positive off cycle. So we know that when Vi is less than of V gamma, so means what is the V gamma value? Either that is 0.7 or 0.3 based on the type of material. If I consider the silicon diode, and this is applied input voltage, and this applied input voltage contains a magnitude is Vm. So cut-in voltage is only the 0.7. Hence, if the Vi is greater than V gamma, diode acts as your forward bias. If it is a forward bias, the current is flowing. So what is the relation? We observe V0 is equal to Vi minus I into Ra. So what is the current? When the diode is a forward bias, how much current is the flows here? Just now we observe what is I? I is represented as Vi minus V gamma by R. Hence, here I am going to substitute this one I. So what is I? Vi minus V gamma by R. I am going to substitute this I here. Hence, V0 is equal to Vi minus I means VI minus V gamma by R into R. This R is a get cancelled. VI is a get cancelled. Minus of minus V gamma becomes, so V naught becomes your V gamma. So here, hence, the V gamma is always constant. If the output is a constant, that should be represented as the slope is a 0. And similarly, when if the VI is a less than of V gamma, means let's take during the negative off cycle, what happens here? Diode becomes your reverse bias. So during the negative off cycle, diode becomes a reverse bias. If the diode is a reverse bias, there is no flow of current. Hence, during this cycle, when VI is less than V gamma, the current flowing across the network is 0. Hence, from this mathematical relation, what is the output relation? V naught is equal to VI minus your I into R. During the negative off cycle, the current is represented as 0. Hence, what is the V naught? V naught is equal to Vi minus 0 into R. So, hence, V naught is directly proportional to your Va. So, here, what is the output voltage? The output voltage is directly proportional to your applied input signal. Means, this input signal is linearly changes with respect to your time period. So, hence, output is also linearly changes with respect to your time period. That is the reason the slope is represented as 1 here. So, at this point, the slope is represented as your 1. So, based on these two analyses during the positive off cycle and during the negative off cycle, here now I am going to draw the graphical representation. So, this is called as the transfer function of the clipper. So, for this case, let us consider, and let us take this is the x-axis and this is the y-axis here, and this is my given input signal, or otherwise you can consider like this. Let us take this is your applied input signal Vi, and now I am going to observe the graphical response here. So let us take this is again time period, x-axis is the time period and y-axis is the output, and here I am going to draw the output voltage. And what we observe during the positive portion, diode becomes a forward bias. Hence, it is replaced with a short circuit. That is the reason we observe that output voltage is equal to V gamma under practical condition. So, or in ideal condition, it should be assumed as 0. But in a practical condition, we consider that when the diode is a forward bias, the output voltage across the diode is represented as your cut-in voltage. What is the cut-in voltage? Here we consider the silicon diode. Hence, V gamma that is equal to 0.7. So, hence 0.7 means it is nearer to the 0 volts. Then similarly, what happens during the negative off cycle? So, during this duration, negative off cycle duration, so here the diode becomes reverse bias based on your circuit construction. So, if the diode is a reverse bias, what happens here? It is replaced with the open circuit. Hence, the output voltage during the cycle, the output is equal to your input signal. So, hence, that is represented as your input signal. So, from this, you can observe this is the graphical response of a clipper circuit. If you observe this graphical response of an output signal, so what happens here? It removes the positive portion of a given input signal and it allows the negative portion of your given input signal. That is the reason from this response, this clipper circuit acts as a positive peak clipper with a 0 reference voltage. So similarly, now we are going to observe a negative peak clipper with a 0 reference voltage. So for this case, just I'll modify the diode utilization here. In a previous circuit, we use that anode is connected to positive signal of your given AC signal. But here, the cathode is connected to this side here with respect to your anode here. Now we'll see what happens here. So during the positive portion as well as during the negative portion here, let us assume we are applying the input signal. So what is the input signal here? The input signal is represented as Vp sine omega t. During this cycle, let us take a input signal is passing through this network, and during the positive off cycle, so what happens? The positive signal is connected to cathode side with respect to your anode, means anode is connected to negative pole. And we know that in a diode, If anode is connected to negative energy with respect to the cathode, we can say that diode. So under this positive portion, what happens? Your diode becomes your reverse bias. Under this condition, diode becomes your reverse bias. If the diode is a reverse bias, what happens? What is the equivalent circuit? Now I'm going to draw the equivalent circuit. And during this applied signal, during the positive portion, and here diode is replaced with open circuit, and this is R. Now let's take this is RL. Let's take this RL. Now we are going to observe the V0. So if the diode is an open circuit and this output voltage is directly proportional to your given input signal, hence the V0 is equal to your V in signal. Similarly, during the negative off cycle, so what happens if the negative CP is passing through this diode means, so negative energy is passing to cathode with respect to anode. So hence, during this negative peak, diode becomes, we know that if anode is connected to positive energy, we can say that diode becomes your forward bias. If it is a forward bias during this negative peak of signal, what is the equivalent circuit? This is R, and diode is replaced with a short circuit. In a practical condition, it contains short circuit along with the cut-in voltage. Now, but we need to observe the diode representation. Cathode is connected to top side, hence the negative pole like this, and this is V gamma. And now we are going to observe the output voltage. From the circuit, what is output? This is negative polarity, this is positive polarity. So if you consider the ideal diode, it is simply replaced with a short circuit. So if it is ideal diode, the output voltage is represented as a 0. But here I consider the practical diode. Here the practical diode is replaced with a short circuit along with the cut-in voltage. But here I drawn the different ways. So negative is connected to upside and positive is connected to ground. Why? Because of the anode is connected to ground node and the cathode is connected to this output node here. Hence, I drawn like this. So from this, what is the output voltage? This output voltage directly proportional to this one. Hence, V0 is equal to minus V gamma here. So hence, during the positive portion of the given input signal, from this circuit, the output voltage is directly proportional to your input voltage. During the negative portion of your given input signal, from this circuit, the output voltage is equal to negative cut-in voltage. So here the cut-in voltage is either 0.7 or 0.3. 0.7 for silicon and 0.3 for germanium. So based on this analysis, so here I shown the output response of a negative peak clipboard with a 0 reference voltage. So why with that? What we observed here during the positive off cycle, so here it allows the V0 is equal to V in, and during the negative off cycle, so output voltage is equal to only the cut-in voltage. The cut-in voltage is negative cut-in voltage, hence it is represented as minus 0.7 here. Now coming to your mathematical analysis from this circuit, how to write this one again, and let us take this is the Vi. So means Vi is equal to the voltage drop across this resistance is IR, and here if it is a forward bias, it should be represented like with the short circuit, it should be replaced with equivalent model is V gamma. Hence, but this polarity is minus and plus, hence it is represented as minus V gamma. From this relation, we should observe this I here. So I is equal to Vi plus V gamma by R. From this representation, we observe that the current equation, the current is Vi plus V gamma by R. Again, from this circuit, the output voltage V0 is represented as minus V gamma. Hence, I am going to define this one. Vi is equal to I into R minus this one is represented as your, so V0 here. Hence, so V0 is represented as, so how to write this equation here? So V0 is represented as Vi minus your IR here. So you just can substitute this V gamma is replaced with V0 minus V gamma is replaced with V0. Hence, V0 is equal to Vi minus your IR here. And by using this mathematical relation, now we can observe. So what happens if the Vi is greater than V gamma? So what happens here? So more voltage across the cathode here. So what happens here? If the anode voltage is larger than the cathode voltage, then only we can say that diode is a forward bias. If the anode voltage is less than of a cathode voltage, we can say that diode is under reverse bias. At this point, if a Vi is greater than Vr, means the more voltage across the cathode side compared with the anode side, hence diode is acts as your reverse bias. So if the diode is a reverse bias, the output voltage is represented as your V gap, V in here. So the diode is a reverse bias, the current flowing across this network is represented as your zero. So what is the mathematical relation here? The V naught is represented as Vi minus I into R. Hence, so V naught is represented as Vi minus I into R. So when the input signal is greater than of V gamma, diode is acts as a reverse bias. Hence, the current flowing across this network is represented as 0. Hence, V naught is equal to Vi minus current is represented 0 is a product with R. So 0 into something 0. Hence, V naught is directly equal to Vi. So yeah, what happens? V naught is equal to Vi, where Vi is linearly varies with respect to time. Hence, the slope is represented as 1. Similarly, if a Vi is less than V gamma, so means if a Vi is less than V gamma means so more negative voltage you are applying, and here this is connected to positive voltage. This is ground means 0, and here this is a 0 volts and this is a negative voltage. So what happens here when Vi is less than V gamma means anode voltage is greater than of cathode voltage. Hence, diode becomes the forward bias. So if the diode becomes a forward bias, it allows the flow of current. Hence, it generates the current here. So what is the current? V naught is the output voltage represented as Vi minus I into R. So what is I? We observe the I is observed as Vi plus V gamma by R. Just can substitute this I value here. So here from this V naught is equal to Vi minus this is Vi plus V gamma by R into R. So this is I value. So what is I value? Vi plus V gamma by R. So R is a get cancelled. Vi is a get cancelled. V naught becomes minus V gamma. So that is the reason. If the Vi is less than V gamma, diode becomes a forward bias. Hence, it allows the flow of current. That current is represented as Vi plus V gamma by R. Hence, the output voltage is represented as your minus V gamma. So entirely during this negative half cycle, the output voltage is a constant that is equal to cut-in voltage of PN junction diode. Hence, the slope is represented as 0. Based on these two analysis, mathematical analysis, now we need to draw the graphical representation here. So here, let us consider. So, and this is your applied input signal Vi. Let us take, and now we are going to observe the output response based on the circuit utilization here. So here I use this one. So, and during the positive half cycle, what happens here? Diode become, according to our circuit construction, during the positive portion of a given input signal, diode is acts as your reverse bias here. Hence, the output voltage is represented as your V. Just you can observe this one. If the Vi is greater than a V gamma, so means during the positive half cycle, your input voltage is greater than a V gamma, diode becomes your reverse bias. Hence, the output voltage, here it is represented as your V. Hence, so output voltage is directly proportional to your input voltage. And similarly, during the negative portion of your given input signal, diode becomes a forward bias. Hence, we observe that output voltage is equal to cut-in voltage, but the magnitude of the cut-in voltage is here negative. Hence, during this negative half cycle, what is the cut-in voltage? Here I consider the silicon diode. So hence V gamma is 0.7. But the magnitude of this cut-in voltage is negative. Hence, I consider this voltage is minus 0.7 volts. Hence, so entire this during negative peak half cycle, the cut-in voltage or the output voltage of clipper circuit is only the minus 0.7 volts. So from this output response, the given clipper circuit allows the positive portion of a given input signal and attenuates the negative portion of a given input signal. Hence, this type of the clipper circuit is called as negative peak clipper circuit with a zero reference voltage here. So up to this point, today we observed that what is a clipper and what is a positive peak clipper and a negative peak clipper. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.